Hello everyone. Today I want to give an introduction to linear algebra, basically material from 1.1 to give you a sense of what this class is about, what linear algebra is about. So if I had to answer the question what linear algebra is about, it would be about studying what are called systems of linear equations. Okay, so that's my one-word, one-sentence answer to that question. I guess we can pack it up. We're done for the day. Now, it turns out this kind of innocent-looking statement has a rich theory that we'll explore this semester. What I first want to do is define some of these things. So what is a system of linear equations? First of all, a linear equation is something you've probably seen before. Let's say in variables x1, x2 through xn. This is just an equation of the form, let's see, a1 x1 plus a2 x2 plus dot 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 plus an xn equals, let's say, b. Okay, so the point here is that I've got variables, right? So maybe this is a little bit new to some people. We usually talk about variables as x, y, and z maybe, but we want to deal with arbitrarily many, so I'm going to call them x1, x2 up through xn. And then the idea is a linear equation just says, well, I can put numbers in front of each one here. So I should say where each ai is a real number, and these are called the coefficients. Okay, so the point is I can take these variables and I can multiply each one by a real number. It could be 0, so it actually will make that disappear. And then I add up all of those scaled variables basically, and I set this also equal to a real number. So b is also a real number. And so in some sense, these equations are the simplest you could hope for. Now let me just give you an example. So e.g., I don't know, 2x1 plus root 3 x2 plus, x5 minus 4x6 equals pi. That's a linear equation, right? Because I've got each variable times a real number. Now, x3, it so happens, has 0 in front of it, as does x4. That's allowed. What's not linear is when I'm start multiplying the xi's together. So not linear example would be something like, 2x1 plus x2 x3, or something like, x4 to the 4th power equals 5. So this is a problem. This is a problem because I've taken a variable times another variable. Here I've actually taken that variable times itself 4 times. So linear means I can only have each variable appearing, on its own times a coefficient. Okay, so that's a linear equation. Now, what's a system of linear equations? That's my other kind of key word here. So a system of linear equations is just a bunch of them, is a collection of such equations. So it's just, I have a bunch of them. So e.g., let me just give you a small example that we'll work with today. So I'll just give a real simple example. x1 minus 2x2 equals minus 1. And let's say minus x1 plus 3x2 equals 3. So this is 2 equations, right, because I have 2 of them, in 2 unknowns or variables, right, unknowns. Or maybe I'll sometimes say variables, okay? So that's the idea. That's the basics of what a system of linear equations looks like. And so what are we going to do? We're going to study these. And so what does it mean to study? I should say that, something like this, hopefully you guys have seen before. I mean, this is, probably in pre-calculus even, or, even before in high school or junior high maybe. You've seen systems of linear equations that are, of this sort. And, maybe you call this x and y, like I said, but you should have played around with these before and been able to solve them. What that means is, what are the values for x1 and x2 that work? So let me just say this as a definition, a solution to a system of linear equations. So I'm going to start just saying system now instead of writing out system of linear equations, but okay, so I'm sort of halfway there here. What is the solution? This is a list, let's say, of numbers, I don't know, S1 through Sn, that, makes each equation, let's say, satisfied. So again, let me just go to this example here. This one that we had, x1 minus 2x2 equals minus 1, minus x1 plus 3x2 equals 3. So this has a solution. Let's see, I wrote this down already. So it has solution 3, 2. So when I write 3, 2, what I'm saying is that, this is x1, this is x2. And I know that because, I have two variables here. And so my solution should have a value for x1, a value for x2. Why does this work? Well, if I look at this first equation, I plug in x1 equals 3, x2 equals 2. This indeed equals minus 1. That works. If I look at the second one and I plug in x1 equals 3, it's minus 3 plus 3 times 2. In fact, that does equal 3, right? I'm plugging in x2 equals 2. We're good. So that's a solution. And, and so that's kind of what our goal will be, to look for solutions. So given maybe we can just say this, our goal will be, given a system of linear equations, what are all possible solutions? And in fact, we'll see in a second, these won't always exist. So actually the first question will be, what, does there exist any? Is there any solution to the system? And one more piece of notation, let me say the solution set is the collection of all solutions to a system. So let me give you an example now of what solution sets look like, with a kind of, continuing this example here. And we'll see that there's actually some geometry behind the scenes here. So let me call this kind of a geometric perspective. So one nice thing about linear algebra is that, it is algebra, right? It's kind of symbolic manipulation and solving equations, but in fact, there's some rich geometry behind the scenes, and it allows you to, in some cases, to picture things and use your geometric intuition. So let me just go back to this example. So e.g., back to our example. All right, so this is my go-to example of two equations in two unknowns. And let me actually just start some notation also while we're here, that I'm always going to be thinking of, in general, I'm going to be thinking of m equations in n unknowns. So that's going to be our convention. I just want to start that now, that, here we have two equations in two unknowns. I'm going to talk about m equations in n unknowns as we move forward. So what is this? If I have two equations in two unknowns, as you might know, this corresponds to, in this case, this corresponds to two lines in the two-dimensional plane. Okay, so what do I mean by that? Well, if you look at this first equation, right? So if you look at this equation and let's solve for x2. So this means minus 2x2, well, let me write it this way. 2x2 equals x1 plus 1. So in other words, x2 equals 1/2 x1 plus 1/2. That's a line, right? Again, you might be used to y equals mx plus b, but this is now, x2 equals 1/2 x1 plus 1/2. The second one, if I solve for x2, this will be 3x2 equals 3 plus x1. In other words, x2 equals, what is this, 1/3 x1 plus 1, right? And so this is another line, and what does it look like? Well, in a picture here, what this looks like, let me draw the x1, x2 plane here. Maybe I should use some colors here. Let's see if I have. Okay, this is a blue pen. Okay, so let me draw this first line in black. So this is a line with slope 1/2 and intercept 1/2, right? So maybe exaggerate things a little bit. This is 1. So this line goes through 1 and its slope is 1/2. So let me draw it kind of like this. That's line 1, okay? And then this one I'll draw in blue. So I'm going to draw this one in blue. So the blue line, the blue equation is a slope of 1/3 with y-intercept 1. So I'm going to exaggerate this a little bit and draw it, so it has slope of 1/3. It's a little bit less steep than the other line. But, more or less, bear with me, the lines are not quite straight. But, what this is looking like is two lines in the plane. That's what I'm trying to get at. And what is a solution set? So what's a solution now? Well, it's a choice of x1 and x2 where both lines, are satisfied, the equations defining those lines. So in other words, a solution is an intersection point. Okay, and so you can check, right, in this case, there was one intersection point, and you can check that going back to my, previous page, we saw that this was 3, 2. So this solution is really geometrically the intersection of these two lines, okay? Now what I want to say briefly is what else can happen with a 2-by-2 system with two equations in two variables? Well, let's just think geometrically now. So I'll try to do them both here. There's actually two other things that can happen. So, so we have these two lines intersecting. You can also imagine that you have two lines that are, if they don't intersect, they're parallel. So if you have two lines that happen to be parallel, I can write down, for instance, if you take x1 minus 2x2 equals minus 1, and minus x1 plus 2x2 equals 3, say, you can check that these will be parallel lines. It's not so important, the equations, but you know what parallel lines are. And what is the intersection here? Well, by definition, they're parallel. So there's no intersection. That means that no solution, okay? So here we had, let me just emphasize that here we had one solution, one and only one solution, sometimes called a unique solution. And then in the other case, maybe this is a little bit weird to think about, but what you can think is that in the last situation, I actually have a line, and then I have another blue line that's actually on top of it, the same line. Okay, so let me just give you an example here that you have x1 minus 2x2 equals minus 1. And I don't know, another one that looks different but actually gives you the same line is this. You can see that this is just a negation of that equation. And what's going to happen here? Well, again, the solution set is all intersection points. Well, how many intersection points do we have? We have this, right? An infinite number of them. So you have an infinite number of solutions. Okay? So just in this kind of baby example of just two lines in the plane, we see one solution, no solution, or an infinite number of solutions as your possibilities. I just want to end with an important fact here that we'll see kind of throughout the semester, actually, is that any system of m equations in n unknowns or variables can have it's this trichotomy. These three things can happen. You can either have no solution, you can have one and only one solution, so one unique solution, or infinitely many solutions. Okay, so if it has no solution, we sometimes say this is inconsistent. In the case of one unique solution or infinitely many, we say this is a consistent system. Okay, so this is an important thing that we saw in the case of 2x2s, and this is going to be a fact that holds for any system of m equations and n unknowns. You have no solution, one solution, or infinitely many. You can't have just 14. If you have 14 solutions, that means you in fact have infinitely many. Okay, and so the theme going forward will be, which one of these situations am I in? And we'll talk about that next time.